Lab number 7 is entitled PSpice Macromodeling. The purpose of macromodels are an attempt to capture linear and nonlinear performance of integrated circuits with a much simplified equivalent circuit. Macromodeling is an area of virtual design where we use SPICE components as parts, and our design task is to recreate the reality of the part in lab. Your tasks in this lab is to measure some of the parameters needed for the PSpice macromodel of an op-amp. In earlier versions of the PSpice program, they had another program called the parts program, where you gave parameters of an op-amp and it kicked out the values of the components in their macromodel. The parts program no longer exists, but I was able to break down the formulas that they were using in the parts program. Now we looked at a lot of parameters of an op-amp. Not all of them are used in MicroSim's model, but the ones that are an average slew rate, the input biasing current, the open loop gain at low frequencies, the gain bandwidth product, the unity gain crossover frequency, the phase margin, which is measured for a gain of 1, a common mode rejection ratio, AC and DC output resistance, short circuit current positive and negative, saturation voltages positive and negative, and the power dissipated by the IC. I solved for all the formulas and broke it into a design procedure. I won't go through this here. I've actually gone through it in supplemental problem 5.3, so I'd refer you back to that part of the ebook, which is in chapter 5, the supplemental problems, to see the techniques for applying these parameters to these formulas that are given here. These formulas go on for 2 more pages, so let's jump to page 3 and take a look at measuring some of the op-amp parameters. Now in our class notes in chapter 5, we tested an op-amp macromodel in many open loop configurations. That's easy to do on a computer because there is no noise in a computer simulation. But in lab, if we had 70 microvolts of noise and multiplied that by 200,000, we get about 14 volts. That's basically the saturation voltages of our op-amps. So we can't take any measurements in lab open loop unless you apply some really tricky techniques to be able to measure anything. So we're going to do something quite different. We're going to measure closed loop circuits and work backwards since we derived the formulas. Let's first take a look at measuring the open loop gain at low frequencies, which is called ADM 0, which means it's zero frequency. The technique here is that we're going to make ADMO a smaller number by using a voltage divider. So here's a proposed circuit for measuring ADMO, and I'm going to put an input signal here that's at low frequencies, maybe around 1 hertz or so. And then the output voltage here is going to be equal to the voltage across these terminals, or device under test, our op-amp that we're trying to test. It's going to multiply it by the open loop gain. But because of the sign change here, it's going to be a negative value. But what's the voltage V1? Well, since no current roughly goes into here, we have a voltage divider of the voltage V sub x times 100 over 100 plus 100K. That's about 1/1000. In other words, V1 is about 1/1000 of V sub x. So now if we solve for ADMO, it's going to be equal to V out. Bring the center side of the equation, so we're going to be multiplying by 1,000 and then dividing by V sub x. And that's the equation that you see over here. So by measuring the ratio of V out to V sub x and multiplying that by minus 1,000, or just take the magnitude of it, you get the value of ADMO. Now when you measure this in lab, you may find something quite surprising. In our data sheet, it says that ADMO is around 200,000. Well, that was for the 741 op-amp in 1968. They improved on the design in the 1970s, but still called it the 741 op-amp. So you may find that this number is a lot bigger than what it was in the 1960s. I want you to see that as you take the measurements. Next, I'd like you to figure out how to measure the gain bandwidth product, the unity gain crossover frequency, the phase margin for the gain of 1, and the saturation voltages VSET positive and VSET negative. If you recall from our chapter 4 notes, the non-inverting amplifier had 1 over beta equal to K. So let's use that circuit. Now if we have an open loop curve like this, and we have a non-inverting amplifier with a gain, say, of 100, which would be 40 dB, the closed loop gain is going to look like this, and then it's going to follow the open loop curve down once it runs into it. And F1 would be the 3 dB frequency. So if you design a non-inverting amplifier with a gain of 100 and find the minus 3 dB frequency, then you can simply take the product of these two to get the gain bandwidth product. Now as the frequency increases, we follow the open loop curve down because K is 1 over beta. And so this is the case where we have ADM times beta much, much less than 1. So we can measure the frequency where the gain crosses 0 dB, which would be over here. whatever that frequency is, and we can also measure the phase angle. There was a technique in the 303 lab, lab number 7, for measuring angles. I'll refer you back to that, and then you can calculate the phase margin, which is going to be 180 degrees minus the angle of ADM beta. But for this particular case, the gain is equal to 1 at this frequency, so beta is equal to 1. To be able to calculate the phase margin that's needed for our macro model. Now lastly, if we take this same circuit and lower the frequency below the full power frequency, which is around 10 kilohertz, then we're back in here somewhere, and then we increase the input until the output saturates, we can measure the positive and negative saturation voltages. Now this is based on having a specific power supply, say of 15 volts, so please double check with your digital multimeter that the power supplies are actually set to 15 volts. Next, I'd like you to measure the short circuit currents, positive and negative, the slew rate, and the power dissipation. A unity gain buffer circuit is a unique test circuit in that there is virtually no feedback current. So when we put a load on it, what we see in the load is what's coming out of the op-amp. So suppose we apply a 1 kilohertz test signal to this circuit with a small load resistance. We'll eventually invoke the current limiter. So if we're expecting around 25 milliamps plus or minus, say we put a 100 ohm load on it, then when we hit the current limiter, we're going to be hitting roughly plus or minus 2.5 volts, kind of inducing a clipping voltage. So without short circuiting the op-amp, we can measure the short circuit current by taking the voltage where it clips and dividing by the resistive load. We can do this instead of short circuiting the output of the op-amp because we can't measure current easily with the oscilloscope. Now let's take that small load off and apply a 10 volt peak to peak square wave at around 20 kilohertz. This is actually how the slew rate's measured in the datasheet. Now the macro model that we're using uses a symmetric slew rate, and so what we're going to have to do is take the average of the two. And so the slew rate will be the sum of the two divided by 2. Lastly, the power dissipation of an op-amp is a supply current times the difference of the power supply voltages when there's no load current. Now the power supplies have a mode where you can display the current that's coming out of them, but we're looking at about something on the order of 2 milliamps or so. It's be kind of hard to read. But we do have a DC ammeter in our digital multimeter, and so we're going to use that feature to measure the current that's going into or out of the power supply. I'd like you to connect this in series with one of the power supplies and record the current that will also be what's returning through the other power supply. The product of this current times the difference of the power supplies across the op-amp is the power dissipation of the op-amp. If a load were present, then the power supply would supply the current to the load. As we've shown in class, this is not modeled in the microsim macro model. Next, I'm going to have you measure the input offset voltage, VIO. This is a DC effect, but there's also 2 other DC effects. That is the input biasing currents and input offset currents. So I need to minimize their effects when I'm measuring this. So what I'm going to do is set up a circuit that gives a high gain to this, so I can make the number much, much bigger, and to use resistors that are small enough that the drop across them caused by the biasing currents and input offset current wouldn't affect the answer. So I'm going to take this circuit over here, which is basically a non-inverting amplifier with 100 ohms and 100K, and I'll pick this resistor as we've shown in the notes to have the effects of input offset current be canceled. So I'll pick this to be equal roughly the parallel combination of these two, which is about 100 ohms. Now in our model, the input offset is modeled this way, and so this circuit is going to have a gain for the input offset of 1 plus this resistor ratio. So it's going to be about a value of 1000 plus 1. So if I were to measure the voltage here, it's going to be 1001 times bigger than the voltage that's over here. So we can just take the magnitude of that, and that would be our way to calculate VIO. This next circuit is going to measure the input biasing current, but again I have to worry about the input offset voltage because that's also a DC effect. But I'm going to use basically a gain of 1 circuit, so we're going to multiply that by 1 and make the value of the input biasing current get ramped up by using very large resistor values. Okay, so here I've got 2 switches. Suppose I close this switch, so I short this out, have a gain of 1 circuit, and the current that's flowing in here into the plus terminal will create a drop in this direction, and that'll see a gain of basically 1. So I'll have a value of V out equal to a minus I sub B plus of times R1. Now the minus sign is a little hard to see here, but it actually is in your PDF copy. Now if I close this circuit, the voltage cross here is 0. Let me just erase this. We're going to short this out, close this switch, open this one up, and now the current that's flowing in here is the current that's flowing into the minus terminal. Since there's no voltage cross here roughly, and there's no voltage cross here because of the short circuit, the rise in voltage here is going to be equal to the drop in this direction, which is going to be how our current's flowing. So it's going to be the current going in the minus terminal times the resistor R2. And so we can use those DC measurements with our digital multimeter to work backwards and figure out the plus and minus input currents. The last three things we need for the macro model are the common mode rejection ratio, the DC output resistance, and the AC output resistance. Actually, there won't be enough time in lab to do these measurements. They are a little tricky also. So I'm just going to have you use the ones that are in the data sheet. So we're going to use the common mode gain of 6, and then calculate the common mode rejection ratio using the value of the open loop gain that you measured. For the DC output resistance, we're just going to use 145 ohms, and for the AC, 75. If you were to measure these, they're not going to be far away from this value anyhow. We'd like you to do a pre-lab, so before you come to lab, meet with your lab partner, sketch your test circuits, and decide on element values using the available parts in the parts cabinet. Also list the appropriate formulas found in the class notes that correspond to these test circuits and bring them to lab with you. Now, after you measure the macro model parameters, you're going to put the numbers into the algorithm on pages 2 and 3 of this lab. I'd like you to type and print, if at all possible on one page, the PSpice test circuits found in Chapter 5 on pages 8 and 11 through 19. If you want some practice with the formulas, you could try to take the 741 op-amp parameters and stick them into the formulas and then go back and measure them. Or I wrote a supplemental problem, 5.3, doing that with another op-amp called an LM101. I think I have to point out with the algorithms on pages 2 and 3 of this lab report is that there are 3 parameters that we're using in class that are actually the opposite sign in the macro model. This is going to be the short circuit current negative, the negative power supply voltage, and the negative saturation voltage. These are normally positive numbers in our class notes, but they're actually going to be negative numbers in the macro model formulas. And this is because I developed these algorithms many years before I wrote these class notes. This is explained in extreme detail with things flagged. Supplemental problem 5.3. Make 2 copies of your work. Submit 1 copy of the design to the lab instructor per group at the beginning of lab. This pre-lab will be graded as part of your Lab 7 report. It should be neat, and bring your PSpice files and save them on your M drive. And this is lab number 7, PSpice Macromodeling.